This is a fun little problem. I'm going to show you how to think through it, but then also a way that you can write something down. So let's just begin. Let's say as x goes to infinity, let's just note that x squared goes to infinity, right? As x gets big, x squared gets even bigger. And so, well, as x squared goes to infinity, that means that e to the x squared is also going to infinity. As the exponent gets large, the whole thing gets large, okay? And so now, when I look at arctangent, as the inside gets big, that's really the same thing as the limit as, let's say, t goes to infinity of arctangent of t. You're just studying what does arctangent do as its argument gets large. And well, hopefully you know that one. That's something you should just know. Let's write it down. The limit as x goes to infinity of the arctangent of e to the x squared. This is just pi halves. And that's something we went over in class. Make sure that we know that one. All right, our favorite, a word problem. This is a related rates problem. And when you look at a problem like this, you should, first off, be reaching for a formula. What kind of shape situation am I working with? How can I relate everything together and then take derivatives? Well, what we're talking about a spherical balloon. Maybe I'll use my pencil here to underline that. Spherical balloon. We're talking about volume. So I'm looking for the volume of a sphere. Let's write that down. V equals 4/3 pi r cubed. So that's going to be helpful. Its volume is increasing at a constant rate of 100 cubic centimeters a second. So that's actually telling me what dV dt is. Let's write that down over here. dV dt is always 100. I'm going to drop my units just for the sake of simplicity. Okay, the question is, how fast is the radius of the balloon increasing? Right, let's underline that. So that's what we want. That's what we're after. We should write that down. So that's dr dt. That's our goal. And it says when the diameter is 50 centimeters. And let's realize that that's a specific moment in time. Even though I'm not telling you, this happens at t equals 32 seconds, there is a one moment in time when the diameter of this sphere is exactly 50 centimeters. And let's realize that the diameter is 50 if and only if the radius r is 25. So I'm wanting the rate of change of the radius with respect to time when d equals 50, which is the same as when r equals 25. That's my goal, dr dt. All right, well, what we've said in class when we went over these is it's important that you take derivatives first, then you plug in your constants. You don't want to start by plugging in 125, otherwise you're going to get 0 equals 0 when you take derivatives, which is true, but not extremely helpful. So let's take derivatives first, and I'm going to get, let's switch to black here, so I'm going to get dV dt is 4 pi, 3 comes down, cancels, r squared times dr dt. Now I'm going to start plugging in. I know that dV dt is always 100, and this dr dt is the thing that I want. And so I want dr dt at the moment when r is 25. So I'm going to plug in. I'm going to plug in 100 for dV dt, and I'm going to get 4 pi times 25 squared times dr dt, and I want to specify that no longer is this just a generic dr dt. This is dr dt at the moment when r is 25, which is the thing we're after. Notice here I'm going to avoid actually taking 25 and squaring it. 4 times 25 is 100. Cancel 100 out, and there's 25 left over. So the point is, when you solve this, dr dt evaluated when r is 25 is just, what, 1 over 25 pi. And that's that. Whoops, let's stretch that out there. All right, very good. Let's do one more, and then I'll break this up into another video. A little short one. I'm actually want you to pause the video, and I want you to check your work and think about this one for just a moment before I go over it with you one last time. Hopefully, you didn't say that f prime was 5 e to the 4th minus 5 over e to the 5th minus 5 squared. This is a trig problem. E to the 5th is a constant. This is constant. Ln of a constant is a constant, and so it follows that f prime of x is just 0. All right, let's pause the video and then we'll go from here.